Hello, welcome to another episode of Naked Neuroscience, the podcast exploring the workings of the brain and the nervous system in our bodies and beyond. I'm Katie Haylor. And this month...
I was injured in a road traffic accident in June 2004. I work in hospital, unable to move my left shoulder or forearm at all.
We're peeling back the science of the peripheral nervous system, looking at some of the injuries it can sustain, and taking a closer look at exciting new developments on the horizon for treatment. Plus, we'll be digging into more neuroscience news with the help of some local experts. Let's jump straight into some naked neuroscience news with our friendly neighbourhood academics, cognitive neuroscientist Duncan Assel from Cambridge University and perceptual psychologist Helen Keyes from Anglia Ruskin University. First up, Duncan told us about mind wandering, so make sure you're listening carefully.
The authors are really interested in attention deficit hyperactivity disorder, or ADHD. And one of the symptoms of ADHD is increased prevalence of mind wandering, amongst other symptoms. But of course, we all know that you don't have to have a diagnosis of ADHD to suffer from mind wandering. It's something that we all encounter. They were really interested in understanding the neural mechanisms behind mind wandering and how that might interact with cognitive skills. So they got 185 young adults. They put them in an MRI scanner and they made them perform a task called an NBAC task. It's a very simple short-term memory task. And periodically they would stop the task and they had a series of questions about how well concentrated the individuals were, what they were thinking about, how hard they were working on the task, what their minds were on. So they had quite detailed information about mind wandering. And these were interspersed throughout the task. And at the end of the scanning session, they also rated the subjects for their ADHD-like symptoms. And what they found, really interestingly, was that those who had high ratings of these symptoms, firstly, they would be more likely to mind wander. So that tells us that indeed it is the case that these things vary naturally throughout the population, even in people who don't have a diagnosis. And they found that those people who did mind wander more, they performed more poorly on the visual memory task, on the NBAC task. And then when they looked at the neuroimaging data, they found that areas of the brain involved in what we call cognitive control, so areas in the frontal lobe and areas in the parietal lobe, the connectivity between these areas and sensory areas, like visual cortex, would drop out periodically. And in those moments, subjects were more likely to mind wander, and that's when their cognitive performance would drop. It's a really nice demonstration of how you can link these sort of higher order symptoms that we all encounter and that are very common in kids with ADHD, linking it to a neural mechanism and then thus to a cognitive outcome, which in this case is visual short-term memory.
What would you recommend somebody would take away from this study?
Firstly, it's to say the mind wandering that we experience as a sort of very higher order phenomena that happens all the time actually has some really basic underlying neurobiology to it that we're starting to understand. Secondly, that it happens to lots of people. And thirdly, that it happens to some people an awful lot. And that's because this neurobiological mechanism is more likely to kick in those individuals.
Helen, any comments?
Yes, so you said they noticed a correlation between instances of mind wandering and the dropping of the connection in the brain areas. So which drove which?
Very hard to say. The way that I would think about it is that it's one process that we can analyze at two different levels. So we can analyze it at a kind of experiential level, so they describe the experience of kind of switching off and zoning out. And then at the same time, this underlying neural correlate can be demonstrated. Now, those two things, I think, go hand in hand. There may be some previous mechanism that causes both, but I think these things are just sort of two halves of the same coin.
Thank you very much. So, Helen, you've been looking into a paper about whether or not we should be wearing helmets, particularly pertinent for people who live in Cambridge. These are cycling helmets. What were this group trying to find out?
They were trying to find out whether wearing a helmet would make you take slightly more risks, and they were measuring this by looking at how you perceived distance between you and threatening objects or you and non-threatening objects.
What were these threatening and non-threatening objects?
So in a very realistic setting, it was pictures of a tiger or a shark, as you would commonly encounter in Cambridge. That would be the threatening stimuli. or pictures of safe, non-threatening stimuli such as rabbits, mice, horses, things like that.
Okay, so this is a lab study trying to replicate behaviour perception when you wear a helmet compared to when you don't when you're cycling. What did they find?
So they found that if you wear a helmet compared to if you wear a baseball cap, you did risk compensate. So for objects that you perceived to be non-threatening, such as horses and rabbits, you actually overestimated the distance between you and them. You thought they were further away, which suggests wearing a helmet made you feel safer. You risk compensated. Some good news for helmet wearers is that this didn't apply for threatening objects. So when there was a threatening stimulus in front of you, you readjusted your risk level. It overrode that risk compensation behaviour, and you saw the threatening object as close to you, similar to people in baseball caps. So people in baseball caps saw threatening and non-threatening objects as quite close to them. People with helmets saw threatening objects as close, but safer objects as further away. They overestimated that distance.
So what should people take away from this with regard to their cycling behaviour? Because I certainly would always wear a helmet.
So it does add to the debate in an interesting way, because it suggests that wearing a helmet can be positive. The general worry in wearing a helmet is that we recalculate the level of risk, feeling safer, and therefore we take more risks. So this study is saying, actually, if a threatening situation arises, you will suddenly recalculate your risk, taking into account that threat, and you will perceive things safely. So the presence of a threat will override that overconfidence, is what this paper is saying. However, it also suggests that if you're not expecting a threat, so if you're cycling along feeling quite safe, you will be a little bit cocky and take those risky behaviours. So they're saying you overestimate distance, you take more risks if you feel quite safe as a cyclist wearing a helmet, whereas you don't do that when you're not wearing a helmet. So you can take from that what you will. On the one hand, it's comforting to know if you wear a helmet, you will recalculate your risk perception if a threat is present, but if you don't perceive that threat, you could be engaging in risk-taking behaviours that you wouldn't otherwise engage in.
And generally, how much evidence is there to suggest wearing a helmet can put us at risk?
So there's quite a lot of evidence coming from both cyclists and drivers. So we know that drivers will give cyclists less space when they're overtaking if the cyclist is wearing a helmet. And we know from numerous studies that cyclists engage in much more aggressive cycling, much more risk-taking behaviour when they're wearing a helmet compared to when they're not.
But is it also fair to say that we do know a cycle helmet can make a vital difference if you are involved in a crash?
If you're in a collision, without a doubt, you need to be wearing a helmet. You're wearing a helmet, it's going to significantly reduce the chance of brain injury. The same is also true, though, for pedestrians and car drivers. So if you're a pedestrian, perhaps you should also be wearing a helmet. And interestingly, on a numbers level, if you're in a car accident, let's say you're a driver compared to a cyclist, if you're both in a collision, the cyclist is going to need the helmet more than you. But on a pure numbers level, with the amount of people that are in car collisions every year, if all drivers mandatorily wore helmets, we would decrease the level of brain injury more than if we ask cyclists to wear helmets, because there's just fewer cyclists. And we would probably think it would be a bit mad to start saying drivers should wear helmets.
Duncan, do you cycle around Cambridge?
I do, and I wear my helmet. And I'd like to think I'm reasonably cautious with my helmet on. I guess it's one of those things where there are probably massive individual differences. There are some people who presumably are such cautious cyclists, they'll be cautious regardless of whether they wore a helmet. Whereas there are presumably some people who show a big helmet effect and cycle very differently.
I do insist that my children wear helmets, so I'm a bit of a hypocrite.
Helen Keyes from Anglia Ruskin University ending that interview there, and you also heard from Duncan Assel from Cambridge University. And if you want to read those studies, the references are on the show page on our website. That's thenakedscientist.com/neuroscience.
So what we were trying to do with this paper is to demonstrate the ability to type using brain signals, anywhere between approximately 4 and approximately 8 words per minute, a factor of between 2 and 4 faster than what's been demonstrated before.
Each month, the eLife podcast talks to some of the world's best scientists. Join me, Chris Smith, as I hear about breathtaking discoveries hot off the press. Find the eLife podcast on iTunes or listen and download for free from nakedscientist.com/eLife.
This month, we're touching on the peripheral nervous system. This is the part of our nervous system that communicates with the peripheries, including the limbs, the abdomen, and the heart. It's basically everything in the nervous system that isn't the brain and the spinal cord, otherwise known as the central nervous system. Some peripheral nerves send signals from your brain and spinal cord to the peripheries, like, for instance, the muscles, which allows you to move. Others relay sensations, for instance, from the peripheries to the brain and spine in order for you to sense touch or know where your limbs are in space. And then there's the autonomic nervous system, which controls bodily functions you don't consciously direct, like blood pressure, heart rate, breathing, and temperature. So pretty important stuff. To take a closer look at what peripheral nerves can do, I enlisted the help of some other rather reluctant naked scientists. First up, I challenged intern Hannah to, solely by touch, pick out a 2p piece from a pocket full of different coins.
Okay, so this first one feels quite smooth, but a bit too small for a 2p, so I think it's a 1p. Then... this one, I think 2p is one of the larger ones. I think I'm going to go for this one. No!
So you picked out the 50p piece?
So it's...
How come you picked that one out?
It felt like it was thinner and the larger one, so I thought it would be the 2p, but no.
Harder than it sounds. Now, Hannah was integrating temperature differences, size and shape differences, whether there were ridges on the coins and so forth, all in order to help her make that, admittedly wrong, decision. So what are Hannah's peripheral nerves actually doing? Well, sensory nerve endings stretch out into the skin, and there are different types of receptors on the end, ones that respond to temperature, pain, and pressure, for instance. When Hannah feels, for example, the ridges on a 5p piece compared to no ridges on a 1p piece, those signals rocket up the nerve cables called axons to the synapse, where chemicals move across a gap and the electrical signal continues on through other nerve cells up to the brain, where that information is interpreted. But just how good is the neural resolution in our peripheral nervous system? Time for another test.
Right, Adam, you're up. I'm going to touch your finger, and I want you to tell me how many different points are touching you. Ready?
Yep. That was 1. That felt like 1, 2. That was 2.
Okay, now I'm going to do the same thing on your leg.
Okay.
Ready?
Yep. 1. 1 again. And that felt like 1, 2.
Well, he got it right for the finger touch, but completely wrong on the leg. I was using a pen and a pencil, so 2 points of contact every time. And they weren't even that close together. So what's going on? Well, nerves are concentrated differently in different areas of the body. Fingertips or lips, for instance, have lots of nerve endings and therefore a much higher resolution than, say, the back of the leg. And this makes sense from an evolutionary point of view, as you don't routinely use the back of your leg to pick berries from a bush or to kiss your loved ones. Time to terrorise my colleagues a little more. Some aspects of the peripheral nervous system can be tricked. Let's take temperature, for instance. Now, have you ever wondered why chili tastes hot? In order to see how well Adam and Hannah could discriminate spicy food from hot food, I challenged them to, with eyes shut, taste and identify microwaved pieces of red pepper against pieces of room temperature but seriously spicy chili pepper.
Pick up the fork. There we go.
I'm seeing an issue with this. Actually, I'm not seeing an issue with this. That's the problem.
Okay, I think I found one.
Pick up a piece of pepper, or tried to pick... Hannah's doing pretty well.
I think I've got pepper on there.
Okay, you do have pepper. Adam, you're doing very badly. Okay, you've both got some pepper. Now have a taste. Is this red pepper or chili pepper?
That tastes a bit sweet, so I would say that's a regular pepper.
Regular pepper. Adam?
I'd agree with Hannah. That one doesn't feel particularly spicy. I'm still okay, so let's go with that one being the regular pepper.
Okay. Now, next. I will tell you if you're directing your fork at the same pepper.
Okay. So
Adam, that is the pepper you just had, so try and find another one.
Is it on my fork?
It is on your fork, yes.
Did I get it?
No. Do you want some help?
Yes, very much so.
Okay. What do you think? Hannah just shoved it up her nose. How do you eat?
I'm getting a bit of spice with that one, so I would say that's a chili pepper.
Well, my face hurts now, so yeah, let's go with spicy.
I'm not sure Adam will be going near a Vindaloo anytime soon, so I failed to fool them, but it seems like the chili didn't. Spicy food like chili contains a chemical which binds to a receptor responsible for detecting temperature, in this case, high temperatures. So activating this receptor causes our bodies to interpret chilies as being hot when really they're not hot at all. But knowing that won't stop me from downing water or better still milk after taking on a particularly serious curry. So that's hot. What about cold? Well, it seems a crafty chemical called menthol is also rather good at this molecular trickery. Menthol, you guessed it, can also bind to a receptor normally responsible for detecting temperature, in this case the cold, and this is why menthol-containing mints can make your mouth feel cool.
If you just chew it, it doesn't feel cold, but when you breathe in, you get like a cold breeze coming in, so it's like feels
like a gust of wind in your mouth.
Yeah, it's like a whole storm happening in your mouth, like a cold air.
Okay. And how does this compare to ice chips? Because they're genuinely cold. So if you can fish around in that bucket, there should be some ice.
I'm not sure I really wanted.
There's a tiny little ice chip.
Oh yeah.
Adam's going for it.
Okay, off we go. Cold.
Really cold?
Yes. That. Oh. Yeah.
Really, really cold. Adam looks very uncomfortable. Hannah, you've gone for a more moderate ice chip.
Yeah.
How is it comparing to the cold feeling of the chewing gum?
It's more all-encompassing.
So it's definitely more cold.
Yeah.
I'm going to let you guys digest now. I feel I've inflicted awful things on you. I don't normally do this to my colleagues.
A big thank you to Adam and Hannah for being such good sports. Next time, I should probably just bring some cake into the office instead. So now we've seen what our peripheral nervous systems are capable of, what exactly can go wrong? According to the NHS website, in the UK, almost 1 in 10 people over the age of 55 have some degree of peripheral nerve damage. To find out how this damage occurs, I spoke to Rhys Roberts, a nerve doctor and research scientist from Cambridge University and Addenbrooke's Hospital.
Diseases of the peripheral nervous systems are generally called peripheral neuropathies. There are various estimates, but roughly around 2% of people will have a peripheral neuropathy at any one time, and some estimate that as we get older, it can go up to around 8% of the population. Now, peripheral neuropathies themselves, the problems can be split into two main types. So there are conditions that you've inherited. These are genetic conditions, many of which, as we now are able to sequence DNA much easier than previously, we're able to pinpoint the specific changes that lead to diseases of the peripheral nerve system, but also a very large group which are what we call acquired. So these are factors which have come on from outside then. So within the acquired part, there's a very, very, very long list of other conditions that can lead to peripheral neuropathies. Now, these can be other medical conditions, or they can be certain things that have affected the nervous system, either being exposed to an agent or a medication's been used for another condition which has had an effect on the nerves. By far the commonest cause of peripheral neuropathy that we see is secondary to diabetes. So roughly 2/3 of people with both the type 1 diabetes and type 2 diabetes, which you will have heard of, will have a neuropathy. So this is very common, and if you think how common diabetes and the commoner it gets with time, this is a significant problem. Clearly, to what extent people living with diabetes will be affected obviously varies from person to person, and also how well controlled the underlying condition is. Of course, people with diabetes can often have an affected autonomic nervous system as well, which can have an effect on their blood pressure, on their ability to sweat, and also on their gastrointestinal system.
So why would diabetes cause nerve issues? Because you do hear about people having tingly feet or tingly fingers. Why is this the case?
So that's a very good question. And I think we don't quite understand why diabetes affects the nerves. What we do know is that the nerves are supplied by very small blood vessels, and it has that plays a very important part in the function of the peripheral nerves. Why we know in diabetes that the blood vessels can be affected, and there's certainly a higher risk of cardiovascular disease. So it's likely there's going to be a combination between the high sugar, the dysregulation in fats, and also that effect on the small blood supply certainly to the longest nerves. There's trauma, so when people have injuries and so forth, that can sever the axon of the peripheral nervous system, meaning that the signals can't get across that injury, and anything downstream of that site will either be weak or you'll be numb.
So this is a physical trauma that essentially snips apart, almost like a pair of scissors, snips apart the nerve, and it's actually disconnected.
Correct. And whilst the nervous system and the Schwann cells in particular will react to these injuries and attempt to guide the growing axon back to where it was before, this not only can take a long time, but on occasions the axons won't get back to exactly where they were previously.
So can that result in paralysis then?
Yes. So any structure that was innervated then by these nerves, essentially the signals wouldn't be getting to for example, the muscles. So you'd be weak. The muscles will get smaller, leading to the inability to move a limb or perform a function. And likewise, any signals that came back via that nerve to the spinal cord to convey any sensation and so forth, that would be impaired as well.
Rhys Roberts there from Cambridge University and Adam Brooks Hospital. Rhys explained that the epicentres of the nerves, called cell bodies, sit just outside the spinal cord, with these cables or axons extending in some cases all the way down to your toe. And these axons are surrounded by protective supportive cells called Schwann cells. These wrap around the axons to form what's called the myelin sheath, allowing signals to get all the way from the toe back up to the spine very quickly. This is handy if, say, you tread on a drawing pin and need to react in a timely manner. Now, our nerves are very resilient. They run along limbs where they bend and stretch with our daily movements and conduct the impulses necessary for sensation and movement. But as Rhys mentioned, physical trauma is one case in which nerves sometimes simply cannot take the strain. Back in 2017, Ed Barnes shared his story about a traffic collision on the Naked Scientist main show.
I was injured in a road traffic accident in June 2004. I work in hospital, unable to move my left shoulder or forearm at all. I also found my right wrist and forearm in a full cast. I was left knowing it was a nerve injury, but not knowing to what degree it would affect me. I was unable to care for myself or do anything. Over the course of 9 months of outpatient appointments, my right wrist healed, but my left arm stayed completely paralysed down to my wrist. I'm now able to hold my hand out in front of me and raise my forearm. However, my shoulder is and will remain paralysed.
Ed Barnes there. So what can be done to help people like Ed? Well, the gold standard currently is a surgery called an autograft, taking healthy nerves from somewhere else on the body, usually the leg, and putting them into the damaged site to hopefully regain function. But this means another surgical procedure with all the associated risks, injuring another part of the body, and of course, scarring. Nervous system tissue engineer James Phillips and biomechanical engineer Rebecca Shipley together direct the Centre for Nerve Engineering at University College London. And they've been working on gels which would be implanted at the injury site, encouraging the severed ends of the nerves to regrow.
We're trying to learn from the nerve graft approach and to try and recreate that in the lab, effectively by trying to make an artificial nerve tissue that could be used instead of a nerve graft. So this would have the same support cells and the extracellular matrix that you find in a nerve graft, but it would be made in a lab, so you wouldn't need to go and harvest a bit of healthy nerve from somewhere else on your patient.
What goes into growing a nerve naturally? And therefore, what do you need to put into your artificial tissue to encourage nerves to regrow?
Peripheral nerves do have the capacity to regenerate after injury, but only in the right environment. Now, the right environment is actually the inside of a damaged nerve. So if the neurons have died away, what you're left with is just the support cells and the extracellular matrix that used to be there. Those support cells are called Schwann cells, and they change their behaviours. They now are cells that can encourage regeneration. So effectively what we would need to do is to build an artificial construct which had cells in it that could effectively do the same job as those supportive Schwann cells. And the really important thing is that whilst neurons can regenerate, given the right environment, they do it quite slowly, which means you really need to organise the cells and the materials in such a way that they really will guide neurons directly from A to B. Of course, the challenge, as with all living cell therapy and regenerative medicine, is where you actually get those Schwann cells from.
So where do you get them from?
Ideally, we would just want some of the patient's Schwann cells. The trouble is you can only get Schwann cells from a patient's nerve, and that would involve damaging the nerve. So what we've done over the last few years is explored other ways of getting cells that are either like Schwann cells or we can turn into Schwann cells. So a few things that we've tried have been taking stem cells from different places, for example, from fat tissue, bone marrow, even from dental pulp within teeth, and trying to turn those cells into Schwann cells or Schwann cell-like cells. That can work reasonably well, but of course there are limitations with that. If you take a patient's cells, maybe from their fat tissue, and expand them in culture, that takes a few weeks, and you've no idea whether they're going to work properly. Actually, the most promising cells that we've found are the idea of using what we'd call an allogeneic source of cells. So that means it's a source of cells that's from another patient. Effectively, you could have them already prepared, build your constructs out of them, so as soon as a patient comes in, they can be used off the shelf and implanted immediately into a patient that needs them.
What do these gels actually look like? And also, I'm guessing you need something to hold them together. So what are they bound by? Do they look like jelly?
The cellular materials we make are hydrogels made of collagen, which is exactly what nerves are made of. They do look just like a very small jelly. We take a solution of collagen and we mix it with our cells and we put it into a mold and it sets. And then what happens inside there is that the cells will naturally interact with the collagen extracellular matrix, and by controlling the tension that the cells produce, we can actually then organise the cells to be nice and aligned in 3 dimensions. Typically, the ones we make in the lab for experimental use are about 15 millimetres long and maybe a millimetre or 2 in diameter.
Once this has gone into a patient or a model organism, would the idea be that the nerves will regrow, reconnect, and then what happens to that gel?
Our approach tends to be to use a natural protein material. Effectively, it integrates and then will become part of the body's protein and will be turned over by the body's cells in a natural way. I should add, however, that the cellular gel part of this is just like the middle of a nerve, which is actually relatively weak. The thing that gives nerves their strength and the resilience, it really is the kind of outer sheath part of it. So those need to be a bit stronger and a bit tougher generally so that they can withstand all the bending and stretching that's required. Now that part, we probably wouldn't want that to dissolve or disappear too quickly. We'd want it to stay there and again to integrate and become like natural nerve tissue.
Do you have any problems with things like rejection, which seems to be a really big issue in regenerative medicine?
The response of the body is absolutely critical. For this to succeed well, we really need to make sure that the materials and cells we put in will not be targeted and rejected quickly by the host immune system. One of the other important things, of course, is if you're putting in dense cellular material, those cells, if they don't get oxygen and nutrients fairly soon, then they're going to die. So actually what we need to do is to make sure that blood vessels grow into our artificial tissues as soon as possible so that the cells we've implanted will survive. This is one of the things where we've teamed up with Becky's group, because they're real experts in modelling and understanding what makes blood vessels grow into particular areas and how we can then design our artificial tissues to really exploit that.
So on that note, how do you actually design these gels?
So there's a lot of open questions really around how you should best design one of these repair constructs to encourage growth of neurons and growth of blood vessels through the repair site. And those questions really come down to where you position the cells and where you position the materials to maximise the chance of a good repair. So we use computer-based models to explore different kind of designs and try and predict which ones have the best chance, and then we use that to inform the experimental work in James's labs. It's really quite fundamental components, like, for a start, how many Schwann cells should we put in one of these devices in the first place, and then where we should put them. So one of the really important components that we need to consider is this concept of gradient, so variations in different factors in space, and neurons are very clever in being able to respond to these kind of spatial variations.
How far along are you with them?
Well, we're at a really exciting stage at the moment. For years, the problem for us has been what's a realistic source of cells. Cell therapy technology has moved so fast in recent years, and there's so many things available now. Our lead option, an off-the-shelf cell type that's already been used in the clinic to treat things like stroke, and that gives us a really good starting cell because we know that it's got the right kind of safety profile and has been through some regulatory procedures. You know, they've been used in clinic, in trials. So what we've done is we've taken those cells and we've manipulated them a little bit and used them to build our artificial tissue. And we've been testing that over the last few years in the lab, and it's looking really quite promising. We've actually formed a company to take this forward, so joined up with some clinical partners and commercial sector partners to really try and move this forward through regulatory approval, get some investment in. We've got to take the manufacturing forwards.
Looking ahead, how would you summarise the significance, I guess, of this artificial tissue in terms of a difference it could make to someone who has had a traumatic nerve injury?
Autografts sounds like a straightforward thing. Oh, you just find a nerve that's not really used much and chop it out and use that. But actually, it's a really major operation to strip out a section of nerve. There's always going to be damage at that donor site, scarring, extra time, extra cost for the operation. But actually the big benefit would be the impact on the patient. The surgeon would only be repairing a nerve. They wouldn't also be having to damage what was previously a healthy nerve.
People who have peripheral nerve injuries have already got, a very serious debilitating injury. So if we can find a way to try and repair that without having to cause them any further harm or further surgeries or further scarring, that has the potential to make a real difference.
Rebecca Shipley, and before her, James Phillips there from University College London. And that's all we've got time for this month. Thank you to Rhys Roberts, Ed Barnes, Rebecca Shipley and James Phillips. And thank you also to Helen Keyes and Duncan Assel. And thanks to you for listening to the show. We've got a whole host of neuroscience cooking away for 2019, from understanding epilepsy to whether microbes can influence your mood and much, much more. If you want more neuroscience now, subscribe to the podcast to delight your ears and mind with the whole back catalogue of Naked Neuroscience episodes wherever you get your podcasts. And we're also now on Spotify. And as ever, if there's a particular working of the mind that you'd like to hear about, let us know. Email neuroscience@nakedscientist.com. I'm Katie Haler from the Naked Scientist team. Until next time, goodbye and Merry Christmas.